Hello everyone. Welcome to the SWAM NPTEL course on Mathematical Geophysics. This is continuing module number 6, Wave Dynamics in Geophysics. The present lecture is lecture number 2, Seismic Waves. In this lecture, we cover the basics of seismic waves and their applications. The components of this lecture are the concepts of seismic waves, the types of seismic waves, then we look into the body waves, and finally we look into surface waves and surface waves in part 1 and part 2 respectively. We will discuss a few applications in geophysics. So let us begin. First, let us look into the fundamental concept of seismic waves. What is a seismic wave? The seismic wave is an elastic wave which is generated through sudden release of energy within the earth. Now, this release of energy can be due to an earthquake or volcanic activity, which are natural causes, artificially induced explosions, or other disturbances which are of man-made origin. Thus, the important aspect of seismic wave is that it involves release of energy and propagation of that energy and transfer of this energy within the earth. Thus, the seismic wave can have either natural or artificial origin. Now, for example, look into this diagrams. The study of seismic waves is called seismology. We have the division into two parts, that is natural seismology and artificial seismology. The natural seismology involves understanding the various processes which occur inside the earth, and this is triggered by earthquakes, which are natural processes. Now, artificial seismology involves inducing a source of the vibration, such as hitting the ground with a hammer or other kind of induced explosions which can generate seismic waves. These seismic waves then propagate into the earth as shown by the arrow, and they have different velocities at different materials. On encountering a change in the material such as shown here, there is an induced refraction and reflection of the seismic wave. Such changes in the material properties can occur due to water saturation, for example. Here, sand and gravel are shown as dry materials on the above, whereas below the sand and gravel are water saturated, changing their material property and hence the speed of the propagation of seismic waves, which induces such reflections, which are then recorded on a seismometer. Seismometers are also called geophones, which are placed on the surface of the earth for recording these seismic waves, which are reflected from the interface of various layers having different material properties within the earth's subsurface. Now, as the seismic waves have propagated throughout the Earth's interior, they carry information about the Earth's structure internally and the source of the disturbance. Now, we look into the various canonical type of seismic waves. These are the overall seismic wave categories. However, any seismic observation which are made on the surface using seismometer may be a combination of one or more of these various types. Thus, we look into these fundamental as unique and separated phenomena. The two categories of seismic waves are body waves and surface waves. They are divided in the categories based on whether they propagate throughout the volume of the material or they propagate on the surface of the material. Using this diagram, it can be more better clarified. We can look into the source of the seismic wave located at point P, and we have the surrounding volume into which the seismic wave travels. If the seismic wave travels on the surface, these are called surface waves. Whereas if it travels throughout the volume, it is known as body waves. So seismic body waves travel throughout the interior of the earth, whereas seismic surface waves travel along the surface of the earth only. Now among body waves, the two categories are P wave and S wave. And among surface waves, the categories are Rayleigh wave and Love wave. These illustrations help us understand the characteristics of these waves in a more better manner. First, let us consider the body waves. The P wave is a compression rarefaction wave. The material, as shown here, is broken down into grids to depict the compression and dilation. Now, the compression is indicated by thin structures which are placed close to each other, whereas dilation is the thicker structures. Note that the vibration is occurring along the direction of propagation shown by the blue arrow. The materials vibrate along the direction of propagation. This is the P wave. Now S wave on the other hand have different characteristics. Here the vibration of the material is in the direction perpendicular to the direction of propagation. One can see the difference in the structural deformations that can be induced by these waves. The P wave induced compression and rarefactions, while S wave induces shear. This gives crests and troughs in the material and it deforms the material into a wavy kind. Now coming to surface waves. First, we consider the Rayleigh wave. The Rayleigh wave travels on the surface as can be seen by the deformation of the material limited to the upper surface. Now, if we consider a particle or a small parcel of the material, then its trajectory is circular or elliptical due to the Rayleigh wave. The particle moves in an elliptical circular manner as the wave propagates through the material. This is occurring because the direction of propagation and the direction of the Rayleigh wave displacement is perpendicular. But due to the presence of this wave only limited to the surface, the materials move in circular direction. On the other hand, we have love waves where the materials move perpendicular to the direction of propagation but also in transverse manner. This is the direction of the displacement for a love wave. The love wave is also restricted to the surface only, whereas in deep volume of the interior material, love waves are absent. We can see that the Rayleigh waves induce a circular trajectory, whereas the love waves induce a shearing motion of the materials. We'll look into the details further. First, let us consider the body waves in more detail. The P wave. The P wave stands for primary wave. It is the fastest seismic waves, meaning its speed is the highest among all the four type of seismic waves which we have discussed. Now these are compressional and rarefaction waves, which is also denoted as shown in this diagram. Here we have periodic arrangement of compressions and rarefactions denoted by C and R respectively. The compressions squeeze the material closer while rarefaction diverges the materials outward. Now this keeps on alternating as the wave propagates with consecutively a material vibrating along the direction of the wave. Thus, this type of waves are also called longitudinal waves. The definition follows. The longitudinal or compressional body wave passes through a medium as a series of dilations and compressions. The equation for the compressional wave in x direction is governed by the wave equation with alpha square replacing c square. The velocity of the P waves can be given as A equals lambda plus 2 mu by rho, which can also be written as square root of k plus 4 by 3 mu by rho. Here, rho is the density of the material and k and mu are material properties which are different for different materials. Next, we consider the S wave. The S wave stands for secondary wave. It is a shear wave which is slower than P waves. Since it is a shear wave, it depends on the shearing capability of the material. It can only travel in materials which can withstand shearing. For example, solids. Thus, as fluids such as gas and liquids cannot sustain shear, the shear waves cannot propagate in liquid or gaseous media. The shearing ability of a material tends to amount for the reinforcement or the restoring force for these secondary waves. One can see that the shearing displacements can lead to a wavy nature of the material. Such wavy nature cannot be sustained in liquids or gases, and thus the absence of any restoring force in such medium leads to no propagation of secondary waves. Thus, transverse waves can be described as the wave in which the particle of the medium moves in a transverse direction, that is, a direction perpendicular to the wave propagation direction. This means that the motion of particles is at right angles to the direction in which the energy of the wave is traveling. If beta is the s-wave velocity, then beta equals root over of mu by rho. Now, this is the speed of secondary waves comparing to the speed of p waves, which is given by alpha. We can see that the numerator of alpha is higher than the numerator of beta. Thus, p waves travel faster than s waves. Next, we look into the surface waves. The first part relates to the Rayleigh waves. Now, as we have discussed earlier, Rayleigh waves are surface waves which cause the particles in the medium to move in elliptical manner. Such that the particle motion describes a retrograde ellipse. A retrograde ellipse means that the motion of the particle is clockwise if we look in a direction such that the direction of propagation of wave is towards the right. Thus, looking from this direction such that the direction of propagation is towards the right, we have an anti-clockwise motion, that is the retrograde ellipse. The major axis is in the vertical direction while the minor axis is along the direction of wave propagation. Now, for the Earth's case, the speed of the Rayleigh wave, denoted by Lr, is approximately 0.92 of beta. Remember, beta is the speed of S waves. Thus, Rayleigh wave travel approximately at 92% of the magnitude of the speed of S waves. Now, it causes the ground motion into an elliptic pattern. Using this diagram, we can better understand the Rayleigh wave phenomena. The particle motion is given here. Now, the direction of propagation is towards the right, whereas the depth is towards the bottom. The uniformity of the grids at the depth shows that the Rayleigh wave is only limited to the surface. Now, considering the passage of the waves along these 2 points, we can see that this point is going to experience this heightened position after a certain duration. But due to the fluctuation along the direction of displacements, such as this, the particle is going to undergo an elliptic motion. This would be the location of the particle indicated by red dot in subsequent times as the wave propagates, thus describing a elliptical motion. Now look into the details of surface waves, which are love waves. The love wave causes horizontal shearing of the Earth's crust. Now, horizontal shearing means that the direction of the particle motion is perpendicular to both the direction of propagation and to the depth. If these two are the direction of propagation and depth, the direction which is perpendicular to both these directions is the third axis, which is the direction of love wave. Now looking into this diagram, which is similar to the previous, we can see that at the bottom the grids are uniform, indicating that the love wave does not propagate into the interior. Now these materials have been displaced farther away from the screen, while these materials are displaced towards the screen. This describes the love wave. Now, if we look from the top, the horizontal displacements would look like a wave, which is the love wave. The particle motion is in the direction as shown here, which is transverse to the direction of propagation. Now, thus we can summarize the features of love wave as the particle motion direction being horizontal and perpendicular to the propagation direction. They do not have any vertical or longitudinal displacements. The love waves are typically traveling faster than Rayleigh waves but slower than the body waves such as the P and S waves. This summarizes the characteristics of love wave, which is the fourth type of seismic waves. Thus, we come to the conclusion of the various types of seismic waves. The seismic waves are a typical example of the wave equation solutions in general, for particularly in the context of Earth's interior. These are very vital tools for exploring Earth's interior. They provide insights into the material properties and geological structure which exist below the Earth's surface. The seismic waves also help us to understand the dynamical events such as slow motion of uniformly distributed materials across the ambient material in the subsurface by tracking the seismic wave properties over a length of time. Now, seismic waves include both body waves and surface waves. These body waves and surface waves each have unique properties. Their characteristics are completely different from each other. However, a real measurement or a practical seismometer reading would indicate the mixture of all types of these waves contributing to the displacement vector on the seismometer, which records the displacement of the ground motion over time. The speed and behavior of the seismic wave depend on the physical properties of the medium, such as density, elasticity, and temperature as well. Thus, we have the fantastic example of a very widespread application in geophysics of wave equation in the form of seismic waves, which can be either naturally induced or artificially induced for directed and targeted exploration activities in geophysics. These are the few references which one can look into for more examples and applications of seismic waves and their various characteristics in applications of geophysics. Thank you.